Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 4, Contextual Applications of Differentiation. Today we're talking about topic 4.2, which is about straight line or rectilinear motion. We're connecting position, velocity, and acceleration. Enjoy today's notes. All right, welcome to 4.2, which is on position, velocity, and acceleration. This is one of those lessons that's really important because it ties a lot into physics, which, most of you, if not all of you, took last year. I know some of you are taking this year in terms of AP Physics, but we're going to try to review some of those concepts if you haven't taken it in a while, thinking really again about like what position, velocity, acceleration are and how they're related to calculus. So, Mr. Brust is playing catch with his best friend himself. He throws a tennis ball straight up into the air. The height of the ball is modeled by this function s of t. So again, the height of the ball is modeled by this function s of t, which is equal to negative 4.9t squared plus 18t plus 2, where t is the time in seconds, and s is the height of the ball from the ground in meters. So, for those of you who took physics before, you might recognize, that if we were to track the position versus time graph for this ball, that, the ball is starting at a certain height, say maybe 3 feet off of the ground. It is being thrown into the air, so the height is changing. It's increasing until it looks like shortly before 2 seconds, it's reached its maximum height, and then it starts to fall again until it hits the ground, where it has a height of 0. So the ball gets thrown in the air, it lands, and comes down. For those of you who took physics or an AP Physics, you might recognize that this motion due to gravity, that when we throw something in the air and we model the position versus time graph, it does in fact make this nice parabola, which is great. And that also makes sense because this is a quadratic function, right? Thinking back to Algebra 2. So if that is our position function, what would our velocity then look like? So we know that the velocity is the rate of change of the position. So useful to know in general that the velocity is the rate of change of the position. So in general, if we're talking about the velocity with respect to time, that is going to be the change in the the position divided by the change in time here. And we'll get to that a little bit more here. But in this case, if we're thinking about that, the change in position divided by the change in time is really, in this case, thinking about derivatives, right? It's a rate, right? It's the rate of change. And we know that rate of change is sort of the shorthand of us thinking about what a derivative is. So what do we know from our graph? Well, I'm going to take sort of 3 points here to think about them. Let's take this point right here. I'm going to draw that tangent line to think about that derivative. I'm going to go up to our vertex. I'm going to draw my tangent line and think about that derivative. And then I'll go over here and then draw a derivative. What do we notice about the slopes of these tangent lines? We notice that over here, the slope of this tangent line at this first point appears to be positive, right? And we notice that at this vertex, the tangent line appears to have a slope of 0. And over here on the right side, we notice that this appears to have a negative slope. So I'm expecting that my graph of the rate of change, aka the velocity, is going to start positive. It's going to go through 0 at whatever time this value is, and it's going to be negative. So I'm going to start this graph, if I wanted to draw the velocity function, with where the 0 is. Since this appears to be just shy of 2, maybe like 1.8 or 1.9, I'm going to estimate that is going to be about right there. So the slope of this tangent line, the rate of change at that point, is 0, which means the velocity is 0 there, right? In terms of the context of this problem, that makes sense because if I throw a ball straight up in the air, there's going to be some moment, right? It's going to go all the way up. It's going to stop momentarily. It's going to have no velocity, and it's going to come back down again. So this moment right here at the peak, at the vertex, is going to be when the velocity of that ball is 0. Now it has a positive velocity, right, as it's moving upwards, but that positive velocity is getting closer and closer and closer to 0. And then after that, it has a negative velocity, which is getting more and more negative as it goes along. In fact, if we graph this, interestingly enough, we have a graph that looks like this. So it turns out to be a straight line. and that is our velocity function for this. Going through that point on the t-axis, right, this is velocity versus time, where the velocity was 0 in our position function. So that's sort of nice that those match up, but we notice here that these are places where the velocity is positive, then the velocity is negative, just as we saw here, positive, 0, negative. Positive has a height of 0, and then it has negative velocities after that. Awesome. What would our acceleration be? Well, our acceleration, similar to the velocity, is that the acceleration with respect to time is going to be the change in the velocity with respect to the change in time. And that rate of change is going to simply be the slope of this linear function. Now, the slope, if I were to draw a tangent line of a linear function, is going to be itself. So since this is a linear function, the slope of this is going to be some sort of constant. And for those of you in AP Physics or thinking back to physics last year, you might have some sort of line that looks like this. And I'm being relatively intentional with where I'm putting it. I would expect that this, if this is a problem that's dealing with gravity on Earth, that the acceleration would be around negative 9.8 meters per second squared, which is our acceleration due to gravity on Earth. And so I would expect, if I were to graph the acceleration in this scenario, that the acceleration would be that negative 9.8 meters per second. Now, before we move on to these actual functions, I do also want to talk about the relationships of the way that these graphs look, right? We said that this function here was, I'll do a different color. We said this function was negative 4.9 t squared plus 18t plus 2. In this case, if we know that the velocity is the rate of change of the position, aka the derivative of the position, I would expect that if I took the derivative of this quadratic function, that I would have a linear function. And in fact, if I do that, the derivative of this is going to be negative 4.9 times 2, so that's negative 9.8 t. 2 minus 1 is going to be, so t to the 1, plus the derivative of 18t, which is 18, and then the derivative of 2 is going to be 0. This is a linear function, right? So we have a linear function. This was a quadratic function. It makes sense, thinking about the power rule, right? If I take one of those exponents away from that quadratic, when I take that derivative, then I'm going to be left with a linear function. Well, what happens if I take the derivative again to find the rate of change of the velocity, aka the acceleration? Well, the derivative of this linear function, negative 9.8 t plus 18, well, the derivative of 18 is going to be 0. That's going to go away. And then if we subtract, multiply by 1 and do the power rule on this term, we end up with that the acceleration is simply negative 9.8. And that is a constant function. So if we start with a quadratic and we take the derivative, we get a linear. And if we take the derivative again, we get a constant. And we actually end up with exactly that negative 9.8 meters per second squared that we were talking about earlier. That makes a lot of sense. Awesome. So let's get into what these are equal to then. So the position function, generally in calculus, AP calculus, position functions are normally referred to as s of t. I've also seen them sometimes referred to as x of t. I would read the problem to try to figure out, what they're giving you if they're giving you an equation. But the velocity is the rate of change of the position, so it is the position, it is the derivative of the position function. So it's the derivative of the position function. Velocity is the derivative of position. The acceleration is the derivative, or the rate of change, of the velocity. So a of t is equal to the derivative of the velocity function. Or, if we want to get real crazy, it's the second derivative of the position function. Right? To get from the position function to the acceleration, I can take the first derivative and then take the derivative again. So aka that would be the second derivative to find the acceleration. That is a nice relationship to know, and definitely something that if I were you, I would highlight. Really, the relationship between position, velocity, acceleration is a really important one. And knowing that you can take derivatives to get from one to the other is huge. So let's talk about what we know about velocity in terms of the rate of change of position. Normally in these problems, we are dealing with functions, it's generally referred to what's called particle motion. Particle motion. And what that means in the context of AP calculus is that generally we're talking about an object like a car or even just like a particle that's moving along an axis in a straight line. So your particle might be moving left or right, right? It might be moving left or right, or generally it might be moving up or down. So the particle, for example, it might move, to the right, and then it might move left, and then it might move to the right again. Your particle, if it were on this line, might move up, and then down, and then up again. Depending upon the context of the problem, the key piece here is that it is moving on a straight line, left or right, or up or down, one of the two. So in general, if we know that the velocity is negative, right? The velocity here is negative. The thing that I would think about with these pictures here is that these are set up just like axes, right? Like the x-axis and the y-axis. The right side of this is the positive direction. The left side of this is the negative direction, just like the positive x-axis and the negative x-axis. If we're thinking about the y-axis, the positive y-axis is going to be up. The negative y-axis is going to be down. This is true when we're thinking about moving left or right versus up or down. So if my velocity is negative, that means that my object, my particle, is moving in the negative direction. So that means that the particle is moving left, if it's going left or right, or it's moving down if it's moving up and down. It's moving in that negative direction. So negative direction. Similarly, if the velocity is positive, if the velocity is greater than 0, that means that the particle is moving either right or up, aka in the positive direction. And if the velocity is equal to 0, if the velocity is exactly 0, that means it's not moving at all. So it is what we refer to as at rest, which just generally means it is not moving. So at rest is one of those physics terms that comes up sometimes. That just means that the velocity is 0, that the object or the particle is not moving. Now the average velocity, you actually already know this, just in a different context. So the average velocity of a function, this word average should make you think of average rate of change. From way back in chapter 1, beginning of chapter 1 and in the beginning of chapter 2, we know the average rate of change is simply the slope. It is the slope. So in this case, in the context of this problem, if we're talking about the average velocity, well, it's going to be the change in position, so where the function ends, s of b minus s of a, so where that function, where that object started, so where the object ended versus minus where the object started, divided by the times here, so b minus a. So key piece here is that we're talking about on an interval from a to b. So generally, we're talking about time here. Starts at a, ends at b. So this should look familiar to us, right? This is essentially slope, like it's like y2 minus y1 over x2 minus x1, because we're talking about the rate of change, that average velocity here. It's the change in position divided by the change in time. But what is speed? For those of you who, again, maybe it's been a while since you took physics or you're not in AP Physics right now, speed is simply velocity without direction. So mathematically, we say that speed is the absolute value of velocity. So it's the absolute value. And the way that, we might generally think about this, for example, I might have a car that I'm, driving down a street. If I'm driving 30 miles per hour down the street, my velocity is 30 miles per hour and my speed is 30 miles per hour. If I stop my car and I turn around and go the opposite direction, my velocity, might be like negative 5 miles per hour, right? Because I'm going in the negative direction and I'm going 5 miles per hour, but my speed would still be 5 miles per hour, even though I'm going the opposite way, because speed cannot be negative. I can't have a negative speed. It has to be positive, and mathematically that's because of the absolute values here. We know absolute values make, the insides of those absolute values positive. Nice. A common question that comes up in these types of problems on the AP exam and in our practice is going to be, is the object or the particle speeding up or slowing down? Now, though, there's an easy way to tell it if you have the velocity and the acceleration. If the velocity and the acceleration have the same sign, then we say that the particle is speeding up. We say that the particle is speeding up. So that is if the velocity and the acceleration have the same sign. If the velocity and acceleration have different signs, then the particle is slowing down. So notice here, this is important for us if we're going to make an argument as to whether an object is speeding up or slowing down. Notice that it requires us to have information about the velocity and the acceleration. Specifically, do they have the same sign or do they have different signs? If it's the same, we're speeding up. If they're different, then they're slowing down. Sometimes, you might be given equations to figure that out, and you might need to, look at the signs at a particular time, or they might give you that information in a table, right? We've got some times, t equals -5, 1, 2, and 4, and they give us the velocity and acceleration at each of these. I know that when t equals -5, that because these two signs are opposite of each other, I know that this object is slowing down. Because one is positive and one is negative. Those signs are opposites. Similarly, I have a negative sign for velocity and a positive sign for acceleration. This object is again slowing down at t equals 1. Here, the velocity is 1 and the acceleration is 0.1. Even though this is a very small number that's close to 0, they are still both positive. Because they're both positive, the signs are the same. That means that this object is speeding up when t is equal to 2. And similarly, when t equals 4, even though the velocity is negative and the acceleration is negative, because those signs are the same, this object is speeding up. And what we actually think about in terms of physics in this case is we say that it's speeding up in the negative direction, right? These has a negative velocity and a negative acceleration. It's speeding up in that negative direction while this is speeding up in the positive direction. Displacement, another physics term that's important to know. Displacement is the net change in position. So how far away did you end up from where you started? So, there might, for example, be a scenario where an object is moving along a line, right? We have this line, and my particle might start right here at 0, and it might move along the line, say like 100 units, and then it might turn around and go in the opposite direction, and then end up right here at about 20 units. So it went 100 to the right, it went 80 to the left. And we notice that in this case, if we're talking about the displacement, our starting position was here at 0 and our ending position was here at 20. So the distance between the two of those would be our displacement. That would be 20 units. Whatever the units are in this problem would be the displacement for this problem. A very common way that we think about this is like runners running around a track, right? If we have a track that is a mile long, and the runners are running around it over and over and over and over again. If my runner goes around once, the runners run 1 mile. If they run around twice, the runners run 2 miles. So the distance that it's run would be 2 miles in this case, but the displacement would actually be 0 because the runner is ending exactly where the runner started. So while it is getting distance, the runner is getting distance as it goes around, the displacement ends up being 0 if the object or the person ends exactly where it starts, because it is the net change in position. So displacement is different from total distance traveled. Those are two different things. So, and actually I'm going to highlight that because that is a common misconception, right? Displacement is not total distance traveled. Those are two different things. So definitely useful for us to make sure that we know that they are different and to be thinking about how they are different. Okay, let's get into some practice now that we had a lot of vocab. They're giving us a position. The position aka x-coordinate of a particle moving along the x-axis, is modeled by the function t cubed minus 4t squared plus 3 when the time is positive, where x is measured in centimeters and t is measured in minutes. Find the displacement of the particle during the first 2 minutes. So in this case, if we're finding the displacement of the particle in the first 2 minutes, we want to really think about where, how did the object change, where it ended up versus where it started. So I'm curious in this case what x of 2 minus x of 0 is going to be. This is the ending position. This is the starting position. So we can highlight that as well. So ending position and the start position. So in this case, we're going to want to plug into this equation and figure out what these values are going to be. X of 2, if we do that, is going to be equal to 2 cubed minus 4 times 2 squared plus 3. If we do that, that looks like that's going to be what? 8 minus 16 plus 3. That's going to be what? Negative 5. And then x of 0, the starting position, is going to be what? 0 cubed minus 4 times 0 plus 3. So that's going to be just 3. So what am I going to do here? Well, it's going to be x of 2 minus x of 0. So that's going to be equal to negative 5 minus 3, which is negative 8. And then we're going to want to tie into the units here. So in this case, it's in centimeters, so negative 8 centimeters. And that would be our displacement for this particular problem. What does it mean that this is negative? Well, the fact that this displacement is negative just means it's moved in the negative direction 8 units. And since we're talking about something that's on the x-axis, that just means that this thing moved left 8 units, 8 centimeters in this case. So useful to know in terms if we needed to relate it to the context of this problem. Because it's negative, it's moving in that negative direction, which in this case is left for it. All right, find the average velocity of the particle during the first 2 minutes. As we said before, the average velocity is like average rate of change. It's the slope. So it's going to be whatever x of 2 minus x of 0 divided by 2 minus 0 is. So in this case, we actually know what x of 2 minus x of 0 is. This is conveniently written. We know that that's going to be negative 5 and negative 3. So I'm going to use that information we did in part 1. We know this is negative 5 minus 3, all divided by 2 minus 0. So that looks like it's going to be negative 8 over 2, which is negative 4. What are the units here in this case? Well, we're talking about the velocity, which is the rate of change of the position. So in this case, we had centimeters, but it's centimeters per our time. So centimeters per minute would be our units for this one. And I know that, again, because we're talking about the velocity, which is the rate of change of the position. So I'd expect it to be like miles per hour, right? It's our distance divided by time in terms of units for this one. Great. Number 3, find the velocity of the particle when t is equal to 4. So notice 2 different things. One is asking about the average velocity. Number 2 is asking about the average velocity. Number 3 is asking about just the velocity. If I want to find just the velocity, I'm not taking into account like the slope. I need to think about here the derivative. So in this case, we know that the derivative v of t is going to be, or the velocity is going to be the derivative of the position. So the position function they gave us, right? We know that that's up here. And so we're going to take that derivative. That looks like that's going to be 3t squared minus 8t. And then that derivative of 3 is going to go away. So if I want to know the velocity when the time is 4, we're going to plug 4 into that equation. So it looks like v of 4 is going to be equal to 3 times 4 squared minus 8 times 4. Altogether, that looks like that's going to be 16. And again, we want to tie into the units here because it's velocity. It's going to be, distance divided by time here. So centimeters per minute, just like the units from number 2. So 16 centimeters per minute would be my answer for number 3. Big key difference here, right? Notice in between 2 and 3, that word average velocity, I did a slope. Velocity itself, I used a derivative to take the velocity function and then use that. Acceleration. for number 4, we know is the derivative of velocity. So acceleration with respect to time is v prime of t. And so if we take that derivative, that looks like it's 6t minus 8. And we're going to plug in our acceleration here. So a of 4 is going to be 6 times 4 minus 8. 24 minus 8 gives us 16 centimeters per minute squared, per square minute. And notice here the difference in units, right? Acceleration, it's centimeters per minute. So it ends up being minute squared here. Useful to know. The fact that these are both 16 is just a coincidence in this problem. That does not actually happen on a regular basis, but worked out for this particular problem. All right, number 5, is the particle speeding up or slowing down at t equals 4? Remember, to determine if something is speeding up or slowing down, we're comparing the signs. So compare signs of v of t and a of t at that particular time, at t equals 4. We notice that both the signs are positive. They're both positive velocity and positive acceleration. So because of that, we know that this object is going to be speeding up. So here's what my justification would look like. I'm going to say speeding up at t equals 4, and here's my justification. Since v of t and a of t have the same sign at t equals 4. So it's speeding up at t equals 4 since v of t and a of t have the same sign at t equals 4. This again is a relatively common question on the AP exam. Normally it's like 2 points. One, if you're saying it's speeding up or slowing down, and then your justification would be that second piece. So don't forget to say how you know, especially when they say that word justify here, right? That's a really important piece. That's what we're looking for when we're grading this style of problem. Particle motion from a graph. The figure shows the velocity of a particle moving on a coordinate line. So I'm going to just write that real big. This is a velocity function. We don't want to confuse ourselves and think it's a position function. Sometimes they give us position, sometimes they give us velocity, sometimes they give us acceleration. Each of those would mean different things. So the question is, when is this particle moving right? Well, we know in general that a particle moves right or up, depending upon the context, when v of t is positive, right? That was from our notes earlier today. We know that a particle is moving right when v of t is positive. Since this is the velocity function already, I am just curious when this is going to be above the x-axis. When are the outputs of our velocity greater than 0? So in this case, I notice that this is above the t-axis. This is above the t-axis all over here. So these parts here in blue, those times are places where the velocity is positive, and those would be places where the particle is moving right. Now, where is that? So this occurs on the following intervals. So it goes from 0 to 1, t equals 0 to t equals 1. And it looks like maybe like around 4.5, 4.6 to 7. So, and I'll put union 4.5 to 7. So I'm saying here that between time 0 and 1 and from 4.5 to 7, that this particle is moving right. I'm using my interval notation, which, if it's been a while, we can brush up on how to do that. And I used that little u thing, which again is a union, to show that it is both of those things together. Great. I'll also mention while we're here, notice here that I used parentheses in both of these. That is because, I don't know what's happening at exactly t equals 0, and at t equals 1, the velocity is neither positive or negative, so I wouldn't want to include that because we only want the places where the velocity is positive. So generally in these types of problems, really often they're going to not have any square brackets. They're going to only have parentheses for them. All right, when is this particle moving left? It's going to be the opposite of this. So a particle moves left when the velocity is negative. This is essentially my justification piece, right? It says justify. This is the justification, me stating this. I'm essentially explaining how I know what values I'm picking here. That's what your justification should look like if they ask for it. When does this occur? Well, in this case, we're looking for places where the output of the velocity is negative, aka places where it's below the t-axis. So I'm looking at this part in green, where it is below the t-axis. So this occurs on the interval from what looks like t equals 1 to t equals like 4.5 again. So from 1 to 4.5. Those are the places where the velocity is below the axis. That means the outputs of that velocity is negative, aka that object is moving in the negative direction or left. Now, sometimes in these, for example, you might say that this is like 4.6, 4.7. If they don't give you a specific value, and really for the practice on this, it's okay to estimate. If you said 4.6 or 4.7 here and it's not clear from the picture, you're going to be fine. I would just be careful in the context of the problem if they tell you where it's crossing to make sure they're using whatever value that is. Otherwise, as long as you're within the ballpark, you should be good. When is this particle's acceleration positive, negative, or 0? So I'm going to erase the colors that I have on here. So we'll go back to our original graph. We know that acceleration is the derivative of the velocity. In this case, it's going to be the slope of the graph. So if I have a velocity function and I want the acceleration, right, but since we know the acceleration is the derivative, it's going to be the slope at any given point on this function. So when would the acceleration be positive? So we know it's going to be positive when the slope is positive. So between t equals 2 and t equals 6, this looks like it has a positive slope. So from 2 to 6. It's going to be negative when the slope is negative. So I see that it has a negative slope between t equals 0 and t equals 2, and from 6 to 7. So from 0 to 2 and from 6 to 7, it's got a negative slope, which means that it's got a negative acceleration. And then when does it have a slope of 0 or an acceleration of 0? That'd be places where the slope is 0. There's actually nowhere on this graph where that's the case. You might think, hey, it could be here or here at these points, but you might also remember from previous chapters that these are cusps. I can't actually take the derivative at those 2 points. We don't know what the slope is at those points. The derivative is not going to be 0. If I was looking for places where the derivative is 0, we might be looking for something like this. Something like this where we can clearly see that it's got a horizontal tangent line and it's continuous and it's differentiable and all of those things. So we're going to say here 0, never. So it is never 0 on this. There's no place where the slope is 0 of this velocity function. Okay, when does the particle have greatest speed? Remember here that speed is equal to the absolute value of velocity. So since they gave us a velocity graph, I'm just trying to find out where the biggest output is. We see at t equals 0 that it has an output of 2. We also see at t equals 2 it has an output of negative 2. So the absolute value of negative 2 would also be positive 2. The greatest speed would be either of those places. So greatest speed would be at t equals 0 or t equals 2. Right here, we've got one where the velocity is 2, here where the velocity is negative 2. So the speed here is 2, and the speed here is also 2. Either one of those would be fine in this case. It looks like all of those ones are less than negative 2 or 2 here. So nowhere to have a greater speed. When is the particle speeding up and when is the particle slowing down? We need to justify. So we've already talked about the velocity when this thing is moving left or right. That's places where the velocity is positive or negative, respectively. We've already talked about the acceleration as well. So if the particle is speeding up, we are looking for places, so speeds up when signs of velocity and acceleration are the same. And I'll just answer this for the justified for 11. Slows down when the signs of the velocity and the acceleration are opposite. So justification parts are done for both of these. That's great. So when does that actually occur? So I'm going to actually go back to my graph. I'm going to erase all this stuff that we've added to it. And let's talk about what we see here. So in this particular graph, we're looking for places where first speeding up. So where the velocity and acceleration are the same. Here, I see that the slope is negative while the output is positive. So the velocity is positive, the acceleration is negative. This is gonna, actually I can just write that here for this. So this is a place from here to here where the velocity is positive, but the acceleration is negative. I know that the acceleration is negative because the slope is negative on this part. Here, from there to there, we see that the velocity is negative because it's below that t-axis, and the acceleration is negative because the slope is negative on that interval. Going back to red, from here to here, we see that the velocity is negative because it's below the t-axis, and the acceleration is positive because the slope is positive. From here to here, we see that the velocity is positive because it's above the t-axis, while the acceleration is also positive. Whoops, not negative. The acceleration is also positive because the slope is positive. And then our last part of this graph that we see, I see that the velocity is positive while the acceleration is negative because it's got a negative slope there. So these parts here in purple are places where the object is speeding up, right? Notice the signs are the same on these purple parts of the line, right? The velocity and acceleration the same. And then on these red ones, we notice that the signs are opposite for each of these. And so those are places where this object is slowing down. So if I'm going to put my answer here, we would say that this is going to be, so speeding up on, looks like it's from t equals 1 to t equals 2, and from, what do we say, like 4.5 to 6. And then we would say that this is slowing down where those signs are opposite. That looks like this is going from 0 to 1, and from 2 to 4.5, and from 6 to 7. So that would be where that occurs. So we've hit the justification already for both of those, which means we are finished with these problems. So this is a pretty physics-heavy lesson, but really if you know the definitions from this first page of notes, these questions should all be pretty good. Good luck. I would say practice, try the practice problems, make sure you're checking your answers, and then try out that mastery challenge. Please have a great rest of your day and take care.